of binomial distribution. That's where we left off. I went back and checked our recording and the video, and that's where we left off. So I'm going to pick back up with that discussion. We were discussing this particular example related to a binomial probability distribution, and we were walking through and thinking about whether or not it represented a binomial distribution. We did note that there were a fixed number of trials because it does tell us that we're going to select 20 students. We do have two outcomes because they either participate in the community volunteer program or they do not. So it's kind of a yes, no. It tells us in the problem, and this is usually the case, that the probability that they're going to participate, which is our probability of success, which is represented by P, is 32%. It doesn't tell us, and we don't necessarily need it right off the bat, but it may help us to go ahead and calculate it, the probability that they do not participate, which would be our probability of failure, which is represented by a lowercase q. We can calculate that because it's equal to 1 minus p. So 1 minus 0.32 equals 0.68. So there's a 68% chance that the students do not participate in a community volunteer program. And so then that's kind of where we left off. We need to look at how to actually calculate those various probabilities. The three questions that are on the screen are, what's the probability that exactly or equal to 15 students participate? At most 14 students participate, and then fewer than 8 students participate. And again, we talked last class that there is a formula for doing binomials. It really only works if you have one where it's exactly or equal to something. Otherwise, you have to do multiple calculations. And the calculations are very cumbersome. So we use Minitab to help us solve these problems. I also mentioned, and I'm going to backtrack for just a minute, that this table that's on slide 15 needs to become a great resource for you. If nothing else, I do recommend that you print slide 15 and have this table nearby when you are calculating the binomial distribution, whether that's on quiz 3, on the midterm, and that sort of thing, because honestly, I don't even keep these things in my head. Again, with lots of practice, it becomes kind of routine, but if I'm doing it for the first time or if it's been a while, I'm going to refer back to this table. So again, if nothing else, I would print slide 15. So let's look at this morning, first thing, how to calculate this binomial distribution in Minitab. It tells us in the problem that X represents the number of students who participate in a community volunteer program outside of school. And we know that we're going to survey 20 students at random. And so we need to think about what values can we have for X. Well, it's usually obvious. We can have pretty much anything from up to 20 because we're going to survey. You do have to remember, though, you could have 0 students participate, and then you could have 1, 2, 3, 4, 5, all the way up to 20. Students sometimes forget that you could actually have a response that would correspond to 0. So it is important that you recognize or remember that, because you do need to include 0 as a possible value for X. Okay, so I'm going out to Minitab. I think I already have it pulled up this morning. Okay, so you go out to app.minitab.com like you always do, log in, and it comes up. Okay, the first thing we need to do is enter the possible values for X, which correspond to the number of community volunteers. And so those are our values for X. Again, you never want to enter a column of data without labeling it. So I'm doing that. We said we could have 0, 1, 2, 3, 4. Whoops. 5, 6, 7. Having trouble typing this morning. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So in the column, you enter the values that you could possibly have, all of the possible values for X. And in this case, that could be any value from 0 students up to 20. We stop at 20 because that's the total number in our sample. Then we have to tell Minitab to do the calculations. We are performing calculations. So I go to Calc at the top menu bar, and we are calculating a probability distribution. So I scroll down near the bottom of the list to probability distributions, and I click, and it gives us 3 options. And we are doing, you can't see it, it's behind my little thing. It says probability density function, but that's the selection that I want. And I miss getting it because it's behind my. Well, let's see. Okay, there we go. Okay, so once I select probability density function, it asks me for the form of input. Well, I am inputting a column of values. We will always be using a column of values. Then I have to tell Minitab where the values are located, in what column. We have them in column 1. So I'm going to double click and select it. Then I have to identify the distribution that I want it to calculate, which for us at this point is binomial. If you use the little arrow, it gives you the drop-down menu. Minitab calculates a lot of different ones. We're doing binomial. I then have to give it the number of trials. We had 20 because that's how many we had in our sample. And the probability of success, which is P, in this case is the probability that they participate, is 0.32. It's stated as a percentage and we convert it to a decimal. I usually use display a table because sometimes Minitab is kind of weird and it won't store it in a column for me. So I just usually have it display it as a table. So I click OK. And in the top half of my screen, it gives me the table. And I'm going to copy this table over to a piece of paper so we can look at it together. Okay, so here's our table. It labels it binomial, so we know we've done binomial with n equal to 20 and a probability of success of 0.32. And then it Minitab has calculated using the formula the probability for 0 all the way to 20. Okay. So the first question that were asked in relationship to this question was, what is the probability? What's the probability that X equals 15? Now it has it in this case, it's in symbols as opposed to words. Okay, so, but hopefully it makes sense to you that equal implies exact or exactly. And I'm going to look at my table that's on slide 15. And I can either look for the equal symbol in the symbol column, or I can look for the word exactly. And I find that on this first row. So if I read over to the last column, it tells me what to do to get that answer from my Minitab output. And it says, read results directly from Minitab. So I'm going to use my table that Minitab gave me. And I'm simply going to read the value. My X was 15. And so I find 15 in the X column and I look at the number that's next to it. So it's 0.000085. There is a very, very small chance, for all intents and purposes, it is 0. Okay, but the probability is technically 0.000085. That you would have exactly 15 students participate in a community volunteer program. Questions before we look at the second one? And I got to look at the PowerPoint because I don't remember what it was. At most 14. Okay, so if we look at the second question, and I'm going to copy the table again. Okay, at most 14. So the probability for the second question is the probability of at most 14 students. Now, you could probably logically, if you think about what that phrase at most means, you may be able to kind of figure it out. Okay, at most in terms of that phrase means it could be anything less than or equal to 14. So at most implies less than or equal, which means I could have 0, 1, 2, 3, all the way up to 14. So if you want to think about it logically, that kind of helps you figure out how to work the problem. But there again, also you can use this table. This time we're looking for at most. Okay, so if I look at my table again and find at most, it's the second row, and it says add the results from Minitab for 0, 1, 2, all the way up to X. So what we need to do is it wants us to take all of the values for the probabilities from 0 all the way up to 14 and add them together. And I honestly wish there was an easier way for you to do that, but honestly, with this table, your best option is to add all those numbers together using your handheld calculator. Please do not do any rounding until you get to the very, very last step. So give me just a minute. It's hard to read the numbers and talk at the same time. And okay, so when I get all of those added together, I get 0.99901. Okay, so if I add from the x value of 0 to the x value of 14, if I didn't make an error, I get 0.999901. So there's practically 100% chance that I would have at most 14 students participate in a community volunteer program. Okay, and I didn't take the time to do it here, but you may want to be extra careful when you're typing them in. You may even want to do it twice to verify that you have the correct response. Okay, but I didn't take the time to do that this morning. Okay, let's look at the third one. And again, I don't remember what it was. Fewer than 8. Okay, so the third question asks us what's the probability that fewer than 8 students participate in the community volunteer program. Now, again, you can use kind of your logic, common sense, and interpret what it means to be fewer than. With fewer than, that simply means it's less than. It does not include the equal. So this would actually be 0, 1, 2, 3, all the way up to 7. Because I want to be fewer or less than 8, we don't include the 8. Again, if you utilize the table, which I strongly encourage you to do, and again, in this case, we're looking for fewer than, which happens to be the third row. It tells you add the results from Minitab for 0, 1, 2, up to x minus 1, and it then emphasizes do not include result for x. Okay, so again, it tells you what to do. So we would add together the values for 0 all the way up to 7. And again, it would be nice to have an easier way to do it, but the only way to do it is going to be to add those numbers together. And I'm doing so, trying to type them in. Okay, I see something in the chat, so give me just a second. Oops. Okay, I think, assuming I did not type them incorrectly. Yes, I'll go through that again in just a minute, Jeannie. Okay, let me give you this answer. If I typed it correctly, again, I'm typing fast, it's 0.8076765. So you're looking at roughly an 80% chance to have fewer than 8 students. All right, Jeannie asked if I'd walk through the steps again, okay, to get the table. Okay, initially you enter all of the possible values for x, And the values for X that you should enter should always be from 0 up to your sample size. So for us, we did from 0 to 20. Then we go calc, because we're calculating. Okay. And let's see if I can scroll this down somehow. I wonder if this will go away. Okay, because we want our probability distribution option. So we're going to calculate, and I think it's behind my screen. Oops, sorry. It's the probability distribution, probability distribution. And let's see. Of course, it's behind my thing and I can't see it. Give me just a second so I can try to make this thing. Well, see if I can minimize my screen a little bit. Okay, so we go calc, probability distributions. When I click on it, we want probability density function. Okay, we want probability density function. I'm going to click. And then we have to enter the information. We want the column of values. It defaults to a single value, but I want Minitab to do all of the values at one time. So I tell it I have a column of values. I then have to select where those values are located. We only have one column of data right now, so it's in column 1. So I select it. I have to choose the binomial, tell it which distribution. Again, it defaults to the normal, but I click binomial or click the arrow and it gives me the drop down box. They are in alphabetical order, so I choose binomial. And I have to tell it the number of trials and the event probability. And again, I usually use display the table. You can, again, I've run into issues with Minitab doing it, so I don't usually have it store them. So I display the table and I click OK. And then it gives me that table. It's at the top of the screen. I know that Jeannie, you may be trying to write those down, and that's fine, but let me show you something if I haven't mentioned this to you guys before that might be helpful. If you're in the course in D2L, under the content, there's a folder labeled Minitab instructions. And I have them sorted by modules, so we're in module 1. And I have the instructions for the Minitab binomial distribution. And it tells you, enter the possible values. You go to click, calc, probability distribution, probability density function, and shows you what to input. So I have them kind of already typed up for you. If you want to utilize those, you could, those are available to print. You could make yourself like a little folder or a notebook to have them handy when you're working the quizzes in the midterm and so forth. So that might be helpful. I apologize if I haven't mentioned that before, but you have, again, in D2L under the content, it's the folder Minitab instructions. So you might find that helpful. Oh, yeah, I really wish it would give me that column, but it's for some reason there's some kind of glitch and I haven't been able to figure out the glitch. But do you have other questions related to the binomial? Do you kind of understand the process that you're going to go through or need to go through as far as calculating these probabilities? Do any of you have questions? You can speak or chat.
I wanted to mention this. I know this is not going to be an option like on the midterm, but just an option you can, if you throw those into a Word document and then copy them and throw them into Excel, they're very agreeable and you can sum them up.
Yeah. I will tell you that for the midterm, because we are using Respondus Lockdown Browser, and you can't go out and use Minitab, what will happen on the midterm is if this were the question, I would have this table embedded with the question. So for the midterm, you don't actually have to create the table, but you do have to know how to read it. And there again, that's where you may want to have that table on slide 15 handy to help you with the calculations. Okay. All right.
So we can use the Minitab notes on the midterm, like the instructions?
Yes, I think I have it right now set up for one 8.5 by 11 sheet of paper, but I'm probably going to change that and just let you use your notes because that would be easier, and because we have lots of Minitab stuff. So yes, you'll be able to use those.
Okay. Cool.
Other questions? Another type question you could encounter is you could be asked to determine the average or the expected number of values, and then also the standard deviation for that binomial distribution. So I have the same example here about the community volunteer program, and I have the question, find the average or expected number of students who participate in a community volunteer program outside of school. Okay, so the question itself uses those words average or expected number, but what they're really asking you for is the mean. And I had given you the formula for the mean earlier on Tuesday, but let me see if I can find it, which slide it's on. It's on slide 16. Okay, the formula for the mean and the standard deviation. I'm going to reiterate them here. Okay, so for the mean is your sample size times the probability of success. Okay, the mean for a binomial is the sample size times the probability of success. So we had 20 students in our sample. The probability they volunteer is 32%, again written as a decimal, and I can use my handheld calculator. So I would have 20 times 0.32, which gives me a value of 6.4. So on average, I should expect to have between 6 and 7 students participate in a community volunteer program outside of school. It's 6.4, so if we round it to the nearest whole, it would be 6. If we allow for that extra, it could be 7. That's why I'm saying the average or the expectation could be between 6 and 7 students. For standard deviation for a binomial is the square root of the sample size times the probability of success times the probability of failure. The standard deviation is the square root of the sample size times the probability of success times the probability of failure. So we would have, in this case, we have the square root of 20, because there were 20 students, My probability of success was 32%. If you go back to our discussion earlier, we determined the probability they do not participate, which was Q, is 68%. So Q is 68%. And I'm going to walk this through longhand. So we do the multiplication, 20 times 0.32 times 0.68 gives me the value 4.352, and then I'm going to take the square root of 4.352, and I get 2.0861447. Most times you're asked to round to 2 decimal places. So if I were asked to round to 2 decimal places, the 8 is in the second decimal place. The 6 next door is going to bump it up. So this would be, my standard deviation is approximately 2.09. Questions on the binomial? Okay, so that wraps up then our discussion of the binomial probability distribution, which is a discrete probability distribution. So remember, discrete probability distributions, just to kind of summarize for you, remember that a discrete probability distribution has a countable number of possible outcomes. We can display it as a table or a graph. We normally use a table. Our probabilities are determined theoretically or by observation, and the main two things to remember is that all of the probabilities are between 0 and 1, and the sum of all the probabilities has to be 1. We looked at kind of the generic or general type, and then we focused our attention on binomial. And now we want to turn our attention to the other type of probability distribution, which is the continuous probability distribution. Okay, to remind you, the difference or the characteristics of a continuous probability distribution is that it has an infinite number of outcomes between two given values on an interval. Again, I always kind of picture my mind sort of like a ruler that's got the increments broken down. You know, we can have half inches, quarter inches, an eighth, a 16th, a 32nd. So I always think about that, how that you have those measurements broken down. Typically, the outcomes for a continuous probability distribution are measured. Again, you're using either a ruler, a scale to do weight, a clock to do time. They're measured, they're not counted. And we're looking for the probability over a particular interval or a particular group of values rather than just a single individual value, like we did with the binomial there when we had x is 15 or fewer than 8. So we're looking at the probability over a particular interval or group of values. Definitely with a continuous probability distribution, those probabilities are determined theoretically using a formula for that particular function or equation that models that distribution. And some of those formulas or functions can get pretty messy. So that's why we use the technology to help us. It can be shown most often using a graph, although you could have it in a table form or even a function or equation form. If we got into the function or equation form, we'd have to do some calculus, and I would anticipate that most of you don't really want to do that. So Again, that's why we're going to be using the technology. But again, one of the differences you'll see is the display. And again, for continuous, we tend to use a graph or a picture. The two requirements for the continuous probability distribution are really the same two that we had for discrete. We just state them differently. The first requirement is that the probability of each outcome is between or equal to 0 and 1. And we're basically saying at that point that all of our probabilities have to be between 0 and 1, just like we said when we were dealing with the discrete. These look a little bit differently again because we're doing it with a graph. And so the height of the bar on our graph, or the height of the graph, represents the probability, and it has to be between 0 and 1. The second thing there is that the entire area under the curve, or the total area under the graph of the function, is 1. Now, that looks pretty weird because a lot of times when you see these particular graphs drawn, whether it is an exponential that we're going to talk about a little bit later today, or whether it's the normal that hopefully we'll be talking about next week, or even the chi-square and some of the ones we'll see later in the semester, the graph itself never actually touches that horizontal axis. And so sometimes that really troubles students because it never kind of ends or closes itself off. And again, that can be proven. I could prove it to you, but we would have to do some calculus. And so again, I don't anticipate that most of you want to do that. But the key piece that I want you to get here, and I'm going to be able to show it to you in just a minute, is that the probability of a particular event or a particular interval corresponds to the area under the curve, which quite honestly, the area under the curve is the whole premise of calculus. You're always trying to figure out the area under the curve. And in statistics, that area under the curve is equal to or represents the probability of a particular event. And again, I'm going to kind of be able to show you that one in just a minute. We focus really on a variety, but in this particular lesson, at this particular point at the end of Module 1, we're going to talk about the uniform distribution and the exponential distribution. And again, probably for most of you, this is again new content because we do not usually talk about either of these distributions in the Stat 1401 course. Okay, so this is probably new content. You have likely not seen these before. So let's focus on the uniform distribution for a minute. It kind of helps you to see those properties that we were just talking about. So a uniform distribution defines equal probability over a given range for a continuous distribution. Sort of think about like a random number generator. Every number 0 to 9 has the equal chance or the equal probability of being selected. Okay, so that means, you know, we have, if you think about rolling a die, again, you have 1 out of 6. So you have that equal probability over the range of values from 1 to 6. That's not really continuous because it's whole numbers, but that may help you to relate. Visually, and we'll see this in just a minute, I'll show it to you, but visually the graph of a uniform distribution looks like a rectangle. And with a rectangle, I can figure the area, because we learn in geometry that the area of a rectangle is its length times its width, excuse me. Okay, so we're kind of connecting some things that we already know about. Usually the scenarios that you're given when you're looking at distributions and you're trying to decide, well, is it binomial? Is it uniform? Is it exponential? Usually the scenarios will say something like uniformly distributed or uniform distribution. It follows a uniform distribution. So usually there's no doubt that you have a uniform distribution. The formula, if you will, for defining the uniform distribution is f of x, the function, the graph, is equal to 1 over b minus a, where a is your beginning point and b is your ending point. And that is inclusive. That includes those endpoints. So that we'll have them, we can calculate the mean of a uniform distribution and the standard deviation of a uniform distribution. And there are those two formulas, and we'll refer back to them. I would encourage you, I don't think I have one that's created, but maybe start yourself a list of formulas. You know, write down general, discrete, probability, write down the formula for the mean, write down the formula for the standard deviation. For binomial, do the same thing. Uniform, so you may want to start yourself a formula sheet so that you have them kind of all on the same page when you're working on quiz 3 or ultimately on your midterm. Okay, so I think we're going to dive into some examples here. Okay, so here's the first example. The amount of time it takes for a student to finish a statistics quiz is uniformly distributed between 6 minutes and 15 minutes inclusive. And it does tell us that X is going to represent the time in minutes it takes a student to finish a quiz. Okay, so I want to try to show you, whoops. I want to try to show you what this would look like visually. Okay, again, notice that it does tell us it is uniformly distributed. Okay, let me see if I can just copy this and take it over to a Word document. It might make it a little bit easier for you to see. Maybe, maybe not. Okay, so again, it does tell us very clearly in the problem that we're dealing with a uniform distribution, which means everything has the same probability. Okay, so visually, if I wanted to draw a picture of this, I have my vertical scale and I have my horizontal. The vertical scale is going to represent the probability. The horizontal scale here is going to represent my time, which is in minutes. And it starts at 6. 7, 8, 9, 10, and it ends at 15, inclusive. Okay, now, if we figure the function, the equation for this model, again, using the formula, f of x equals 1 over b minus a. A here is the 6, that's my starting point, and b is the 15. So I would have 1 over 15 minus 6, which I believe is 1/9. That corresponds to my probability. So on my vertical scale, I know I'm going to have 1/9. And I know that all of these probabilities have that same, all of these values have that same probability, including the 6 and the 15. So notice how visually you have a kind of a rectangle. If you want to close it in here, let me give you a dotted line there to see that you closed it in. Okay, so there is a visual interpretation of this problem. Okay, it is a uniform distribution, which means all of the probabilities are the same. So all of the bars on the graph would be the same height. Now, before I move on, let me prove one of my points to you. I've commented several times that the total area under this quote curve, or in this case, under the rectangle, is 1. Well, since this is a rectangle, I'm going to prove that to you. Okay, I've told you that the total area under the curve is 1. Now I'm going to prove it to you. Okay, again, visually, we have a rectangle. And we know from geometry that the area of a rectangle is its length times its width. Well, the length of my rectangle goes from 6 to 15. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. It has a length of 9 units. The width, or the height, in this case, corresponds to the function itself, which was 1/9, or the probability, and 9 times 1/9 is 1. So the total area under the curve, which is a rectangle, is 1. So I've just kind of proven that statement to you, so you don't have to necessarily rely on the fact that Miss Ralston said it. Okay. So let's look at the question. What was the first question? It says, find the probability that it takes a student at least 8 minutes to complete the quiz. Okay. It is helpful, especially with the continuous probability distributions, if you will draw yourself a picture. And it doesn't have to be perfect. I can rough sketch it. I know that I'm going to start at 6 and end at 15. I know that my probability is 1/9 and that I have a rectangle. Okay, so this question says, what is the probability it takes at least 8 minutes? Now, again, you have to know how to interpret at least. At least means it is equal or more than 8 minutes. So if I look at my graph, here's 6, 7, here's 8. So I can have from 8 all the way up to 15 minutes. And so what I really am looking for is this area of this green thatched region. Well, even that green thatched region, guys, is a rectangle. So if I figure out the length, 1, 2, 3, 4, 5, 6, 7, which, by the way, 15 minus 8 is 7. So I have a length of 7. And my height, or my width, is 1/9. And I know that area is length times width. So I have 7 times 1/9. I get a fraction of 7/9. If you want that as a decimal, 7 divided by 9 is approximately 0.7778. 8 when you round to 4 places. So there's about a 78% chance that a student is going to take at least 8 minutes to finish the quiz. This is ultimately the answer you're looking for because this corresponds to the probability. Now that answer should be between 0 and 1. It cannot be negative and it cannot be bigger than 1. So I'm okay. Let's look at another one. Go out here and get the question. Take between 10 and 14 minutes. Okay, what's the probability that students take between 10 and 14 minutes? So again, I'm going to rough sketch yourself a picture. And I don't even have to mark the tick marks, guys. I can go 6 to 15. I just I'm roughing it in, and I know that my probability is 1/9. And so I want to consider between 10 and 14. And again, I can randomly mark 10 and 14, and I want to be between that. So I'm really looking for this blue shaded region, which is still a rectangle. And again, to figure it, I can figure the area under the curve. And again, the area under the curve is length times width for a rectangle. Well, 10 to 14 gives me 4. 14 minus 10 is 4. So my length is 4. My width or my height is 1/9. So we have 4/9. Or again, if you convert that to a decimal, 4 divided by 9, that's going to be approximately 0.4444. So there's about a 44% chance that it takes a student between 10 and 14 minutes to finish the quiz. I think I had one more. Okay, this one's a little different. Okay, the first two, they're asking you to find the probability. This question is different because it's basically telling you what the probability or the percentage is before you start the problem, because it says find the 40th percentile of quiz completion time. So how 40% of the students take how long to complete the quiz. Okay, so this is a little bit different approach, but we're still using kind of the same idea. So here we go. I'm going to draw the picture. We have from 6 to 15. Sorry, a little crooked there. Okay, probability is 1/9. Okay, so we know we have 40% because it tells us that. See right here, it says 40th percentile. So we know we have 40%. And that 40%, the minimum is going to be 6. And there's going to be some point out here that I don't know. You can call it X. Your text calls it K. And between 6 and that unknown value, there is 40% of our value. So it's like they're giving us the area. Okay, if you use the same approach, whoops, sorry about that. The same idea as we've been doing, we're just solving it for a different letter, if you will, or a different variable. We still know that the area is length times width. We're told the area is the 40%. Let's talk about length in a minute. The width is still 1/9. I don't know K, but I have K minus 6. Okay, K minus 6 would tell me what that value is, but I don't know. I'm trying to find K or X, whatever you want to call it. Guys, at that point, it's the same formula. We're just solving it for a different variable, and you got to do a little bit of algebra. Okay, I would get rid of this 1/9 first, so I can do that by multiplying by 9 on both sides. I'm doing good old basic algebra, so hopefully you haven't forgotten your algebra. So I would do 9 times 0.4, which is 3.6. 1/9 times 9 is 1, so that leaves me with K minus 6. And then to finish solving the equation, I'm going to add 6 to either side. Good old basic algebra. And I'm going to carry it over here. 6 plus 3.6 is 9.6, and that equals K. So 40% of the time, it takes students at most 9.6 minutes. Okay, so the 40th percentile is 9.6 minutes. 40% of the time, it takes students at most or less than 9.6 minutes to take the test. Questions? Okay, let me scroll back up here to the very first one so we can talk about how to calculate the mean of this distribution and also the standard deviation. So I have the same scenario. It takes between 6 and 15 minutes inclusive to take the test, and we want to know the average or the mean. Okay, it's a formula, guys. The mean is A plus B divided by 2. Please do not overthink it. It's a plug and a chug. Okay, so we would have 6 plus 15 divided by 2 is 21 divided by 2, which is 10.5. So on average, it takes 10.5 minutes for students to complete the quiz. Then we can calculate the standard deviation. Okay, the standard deviation, and this is the standard formula, is the square root of B minus A squared divided by 12. And it's always by 12. Again, please do not overthink it. This is a straight, flat out plug and chug. So I would have 15 minus 6 squared divided by 12. That's the square root of 9 squared divided by 12, which is the square root of 81 divided by 12. Okay, so I'm going to get the decimal first. 81 divided by 12 is 6.75. And the square root of 6.75 is 2.59807. Again, be careful, because if you're asked to round to 2 decimal places, be careful here, because the 9 is in the second place. The 8 next door is going to bump it, but that also bumps the 5. So this rounds to 2.60. Questions? Okay, I want to try, I've got 14 minutes. I'd like to try to get through the exponential so that you're able to do quiz 3. Okay, so we're going to shift gears and now talk about the exponential, which is also a continuous probability distribution. And again, this one should be new to you. You probably haven't seen it before. A lot of times the exponentials, I'm not sure if they actually say exponential. I think I do try to make a point on the midterm to say this is an exponential distribution. But usually an exponential distribution is concerned with the amount of time until a certain event occurs. Like the amount of time beginning now until an earthquake occurs, or the length in time in minutes that a phone call lasts from the time you start the phone call till the time it ends. The time in months that a car battery lasts. A lot of businesses would use this particular function when you're thinking about like the car battery or just regular like AA, AAA batteries, the tires for a vehicle, you know, because they have kind of a shelf life, or they last a certain period of time. So you're looking at how long. And so it's used widely in that field of reliability, where you're trying to figure out how long a particular product is going to last. One of the primary characteristics of an exponential function is what they call a memoryless mean. And basically what the memoryless mean implies is the chance of an event does not depend on past trials, which means the occurrence rate is constant. You know, the fact that a phone call lasted 10 minutes the first time, and then the second time it lasted 20 minutes, and the third time it may have lasted, okay, the exponential doesn't worry about what happened the first time or the second time. Okay, so the remaining life of the component, if you're looking at a battery, how long that battery is going to last is independent of how old it is. It doesn't take into consideration how long that battery's been used or whatever. It's called a memoryless mean. Now that goes on behind the scenes. Okay. It's not something you have to calculate or anything like that. But we do have, because of that idea of the memoryless mean, we have what's called the decay parameter. You know, how fast, kind of gives you an idea of how fast that particular item is going to lose its shelf life. You know, how fast is that battery gonna decline, or how fast are your tires gonna decline? It's called the decay parameter. It's represented by a lowercase m, good old English letter M, and it is equal to 1 over the mean. Typically, your scenario will again state that it is an exponential distribution. Again, I try to make a point of that. If it doesn't, think about the scenario. Does it have something to do with time and how something is kind of, in a sense, decaying? The other thing is, with an exponential distribution scenario, they usually will give you the mean. And I've given you the formula there for the function itself if you wanted or needed to create a graph. The mean, again, is given in the scenario. And the other unique thing about the exponential is that the mean equals the standard deviation. Okay, so if you know the mean, you automatically know the standard deviation because they're equal. If you know the mean, you can also calculate your decay parameter because it's 1 divided by the mean. That was on the last slide. There's two formulas that we use for exponential functions, and you have to pay attention to whether you're doing the area to the left or below, or whether you're doing the area to the right or above. And so I have those two formulas there. This is one that you're going to do by hand calculation using your calculator. Okay. So again, these are formulas that you may want to write down, and I would make sure that you make a note which one to use for areas to the left or less, and which one to use for areas above or greater to the right. And I've got it written down on a piece of paper, so I'll have it when we work through some problems. Okay, so let's take a look at an example. It says, on average, a certain, whoops, sorry, I toggled off of it. On average, a certain computer part lasts 10 years. The length of time the computer part lasts is exponentially distributed. Okay, so first off, in this scenario, they do tell you that it is exponentially distributed. They also tell you, it says on average, that the average is 10 years. And so then you're asked a series of questions. And to help you make sure you have all the pieces you need, okay, they start out asking you, what is the mean? Okay, remember the mean is given, so it's 10. Well, if I know the mean, I know the standard deviation because the mean equals the standard deviation. So in this case, my standard deviation is 10. My decay parameter, which is represented by an M, is 1 over the mean. So I'd have 1 over 10 or 1/10. It's probably easier to put it in decimal form if you can. All right. Then they ask you a series of questions related to that scenario. Okay, so I'm going to make us a note up here. We had a mean of 10, a standard deviation of 10, and our decay parameter is 1/10. And the first question says, what is the probability that a computer part lasts more than 7 years? Now, I'm not going to draw it perfectly, but I want to kind of give you a picture of what's going on here. Okay, with an exponential, it runs, kind of starts out high and comes down and scrolls out. Okay, and so we know the average is 10, so they want us to say what's going on from 7, and I'm just going to randomly mark where 7 is, and it's going to keep going forever and ever and ever and ever and ever and ever, because remember, this is a continuous probability distribution. So theoretically, it goes out to infinity. Now, I shaded to the right because this says more than. And hopefully just even that rough draft of kind of that picture helps you to see that this one is to the right, because that's going to help me determine the formula that I should use to calculate the probability. The formula for to the right was E, which is your natural number, to the negative mx. Okay, in this case, your x is 7. Our m is the 1/10. So if we plug into that formula that we have E to the negative 1/10 times 7. We use 7 because that was the value that they gave us. So that's e to the negative 7/10. I did that in my head. From there, I'm going to have to use my calculator. So I'm going to pull up my calculator and I'm going to type in. If you don't know, the E is in blue above the button that says LN, which is near the 4. It's in blue, so we press the blue second button and then LN, and notice that the E pops up on my screen. And then I want negative 7, or 0.7, excuse me. Sorry. Negative 7/10, 0.7. And then I hit enter, and it gives me that decimal value. So I have, and let me scribble it down real quick. I have 0.4965853038. Okay. So my answer here would be approximately 0.49658. Again, we normally round to 4 places. Guys, be careful. The 5 is in the 4th place. 8 is next door. It's going to bump it. So this becomes 0.4966. I got 3 minutes, so let me see if I can do one more. Okay, it says on average, how long would 5 computer parts last if they are used one after the other? Okay, so we're going to use computer part 1. As soon as it breaks down, I'm going to start using computer part 2. As soon as it breaks down, I'm going to start using computer part 3. As soon as it breaks down, I'm going to use number 4. And as soon as it breaks down, I'm going to use number 5. It says on average. Well, the average lifetime of this computer part, we're told, is 10. So if the first one lasts 10 years, and the second one lasts 10 years, and the third one lasts 10 years, and the fourth one lasts 10 years, and the fifth one lasts 10 years, and I add those together, I have 50 years. Because I'm using them one right after the other. As soon as one stops, I put another one in. As soon as one stops, put another one in. And they, on average, last 10 years. Okay, I'm not going to get to the last 2 examples, but I would like for you to try quiz 3. I'm pretty sure the question on quiz 3, maybe you can get through. Okay, I would like for you to try it. Okay, if there's issues with those last few questions, then I'll come back and make adjustments as necessary. Okay, before we go, do you have